Hi all, welcome to a session talking about basic structural systems. This is done on my YouTube channel, but is also in collaboration with NUS DOA, where we'll be specifically looking at examples from Corbusier as much as possible. Through this lesson, we're going to be covering some of the basic topics of structural engineering. Understanding what are walls, understanding what are columns, understanding what are beams and slabs, trusses, space frames, arches, dome shells, etc. Where we'll be dividing in 7 groups based on the model perspective, structure, architecture and culture by Corbusier, Sandaker and DJ. So let's jump right in with one of the categories. We'll start with columns. So columns, I'm sure you've heard of in terms of the classical order of things, going from Ionic to Doric to Corinthian. And a column is essentially a vertical structural member intended to transfer compressive load. So for example, a column might transfer loads from a ceiling, floor or roof, slab, or from a beam to a floor or foundations. There are 2 types, and you've got structural columns and non-structural columns. We're going to be looking at the question of what is a pilote and what is a pilaster, which is especially relevant when studying Corbusier. Now, a column in architecture is a solid upright structure designed usually to support a larger structure above it, such as a roof or horizontal beam. But sometimes decoration, well, a pilote is one of these columns or pillars or stilts that lift the building above the ground of water, hence why you would hear it often when it appears. Here's an example of the National Museum of Western Art, where we can clearly see a column, and on the other side, I hope you know this precedent, where's the Villa Savoie with, of course, the pilotis surrounding the building. An example of what a column and a pilaster is, a column will be structurally relevant, i.e. is going to be able to withstand those compressive loads, whilst a pilaster is more of an ornamental feature you would see in classical architecture. Here, as an example, you've got St. Paul's Cathedral. You can see the pilasters from the classical architecture on the sides of the building and the columns in the middle. The idea is to give the impression that is supporting the structure. But columns have been used in various ways. Junior Ishigami and associates, for instance, have worked on this really interesting building where it's essentially loads of columns that are randomly dispersed and very, very close together. Another way you can see columns being used is by, for instance, John Portland with his Etelenki 2. In 1986, he designed a house for himself where the idea of the column was flipped on its head, where the column could actually be used as an ornamental feature. An example of a typical column detail you might see in practice is, for instance, the steel column that's going to be reinforced in some way. So you can see how there's an I-beam in the middle, you've got some reinforcement cages, and then it's filled in with concrete. An example of a typical column detail you could see in, for instance, offices is having the I-beam then encased with something around it, so that aesthetically it might give a different impression. But it is not a structural element. An interesting example, for instance, when looking at ornamentation in columns would be the Allons Liga Cultural Centre by Philippe Starck, where the French designer essentially took this space and remodeled every single column in a completely different style, proving that we have left the realm of structural necessity with these things, and it's more so a question about aesthetic necessity. A very interesting example, especially when we're talking about parametricism, is Michael Hansmeyer's experiments from 3D to actually built form columns, where he uses computer generation to create very intricate ornamentation that would be near impossible to do by hand. Using algorithms and subdivision processes, he's able to create a new language of ornamentation. Now we'll be jumping in the category of walls. The purposes of walls in buildings are to support roofs, floors and ceilings, to enclose a space as part of a building envelope along with a roof to give a building's form, and to provide shelter and security. We'll be looking at 2 categories of walls, load-bearing walls and non-load-bearing walls, such as solid walls, cavity walls, shear walls, partition walls, skirting walls, but we'll skip over green walls and party walls. In the example of Ronchamp, we can clearly see that on the left-hand side there is a use of a solid wall to structurally hold up the roof. Another way of building is using cavity walls, where you essentially have a layer of brickwork and a layer of formwork, and within the middle you have some form of insulation. Now, this is to make sure that there isn't any issues with thermal insulation, moreover that there's a prevention of moisture within buildings. Using the Unité d'habitation in Marseille, Corbusier employed a shear wall, which is essentially a vertical wall that resists in plane lateral forces such as wind or seismic loads. You'll hear this a lot in practice. A partition wall is a non-load-bearing wall that separates the internal spaces of a building. Here again we can see the Unité d'habitation in Marseille, where the partition wall is painted in green. Often the most difficult to detail, curtain walls are non-structural cladding systems for the external walls of a building. They're generally associated with large multi-story buildings, typically office space. Curtain walls only support their own weight and the loads imposed on them, such as wind loads and again seismic loads, which they transfer back to the primary structure of the building. Curtain walls became prevalent in the 19th century with the development of glass panels, but more so in the 1930s where aluminum became the material that was readily used for construction purposes. Here is a building by Corbusier in the Soviet Union, its only one actually, called the Centro Suyos. Built with Nikolai Koly between 1930 and 1936, this was at the time the headquarters for the workers' councils in the Soviet Union. Now, as we see through time, walls have slowly lost their thickness, and that's because we've been able to reduce our U value considerably. Now, the U value, or the thermal transmittance, is the rate of transfer of heat through a structure divided by the difference in temperature across that structure. The better insulated the structure is, the lower the U value will be. Without going into too much detail about walls, I do want to talk about bonds, which is particularly interesting for Corbusier, and how the use of brick in different manners can serve a structural purpose, more of an aesthetic purpose. In this case, I'm pretty proud Corbusier chose an English bond. Now, through history, we can clearly see the change in thickness of walls. If we take a plan from most cathedrals, for instance, Florence Cathedral, St. Paul's, and compare it to the Casa de Musica by OMA using structural glass, we can see how the improvements in material technology have enabled us to have different thicknesses, moreover, better insulated space. It's interesting to note that in common culture, walls are often used, the architectural element, as a form to describe something that would stop you from getting somewhere, stop you from doing something. They're shown in a negative light. And at the time, architects tried to separate themselves as much as they could from the wall and instead rely on other structural elements. Now let's jump to beam and slab. Here's a model to represent a section through the Unité d'Habitation from Le Corbusier, where we can see that the vertical structure is a mixture of columns and walls, with horizontal structure being a mixture of beam-supported slabs and individual beams that support a secondary floor of timber panels supported on steel beams. Beams are structural elements that resist loads applied laterally to their axis. They typically transfer loads imposed along their length to their endpoints, where the loads are transferred to the walls, columns, foundations, and so on. A slab is a structural element made of concrete that is used to create flat horizontal surfaces, such as floors, roof decks, and ceilings. A slab is generally several inches thick and supported by beams, columns, walls, or the ground. We'll be looking at 4 typical types of beam: standard hot roll beams, truss beams, composite beams, and tie beams. Hot roll steel is commonly used to construct steel beams for construction projects. They are typically created by passing steel through large rollers, which deform it into the shape that's wanted, such as HIWSC beams and so on. Other examples being truss beams. We'll be looking at trusses later, but essentially this is a truss. Moreover, composite beams, which could be a mix of different materials such as steel or concrete. A plinth beam, it's quite simple. You will see them used at the base of buildings, or typically for walls, and a tie beam you will see at the top if there's a need for structural support, or they could be seen in post-roof trusses. For slabs, we'll be looking at some of the various slabs, such as flat slabs, conventional slabs, waffle slabs. Sounds nice. A flat slab is pretty simple. It's a slab that doesn't have any reinforcement with beams, and a conventional slab is a slab that looks very similar, but it is held up by beams. Waffle slabs are used because they're great to withhold greater loads and they don't need any beams. You would typically see them with a waffle configuration, so you've got deep grooves that run up. Holocaust slabs get their name from the voids that are within these slabs. They can be very useful if you want to run, for instance, services through them, and typically they're chosen because they're quite lightweight, relatively speaking, and they can be precast. A typical slab foundation you could find is a solid slab raft. Raft because it takes the idea of something that's floating above ground, and the idea is to cover a large surface with a steel mesh or concrete to make sure that all of the loads that are coming onto it, whether it be columns or walls, are able to spread across the surface evenly. Another typical construction detail would be the composite slab, often seen in high-rises or office projects, where you would have a metal decking with concrete poured on top. The reason you want concrete is for fire resistance, moreover thermal storage, and it avoids and reduces floor deflections and vibrations. The reason you want to use a steel decking is for a superior strength weight and stiffness weight ratio, moreover its ease of handling. A typical process to build it, for instance, would be to have a press, create all of the decking is then cut, then the steel is brought to site, a net is placed underneath each one of the beams so the workers can work peacefully. Steel decking is put on top of those beams, and then with a shear stud gun, they're basically shot into the beams so they stay stable. Some kind of mesh is put on top so that when you pour your concrete it becomes more stiff, and then it is cleaned so that it is very smooth. Typically, we're going to see a configuration where a layer of veneered concrete is going to be poured, again called a screed, to make sure that everything is clean on the surface. Interestingly enough, the Maison Domino that we saw before, here an example is the 1914 readaptation in 2014 by the Venice Biennale, actually had a really tricky construction detail where it used loads of hollow blocks, and the issue with that is it created very difficult installation. If potentially a composite slab or solid slab was used, maybe it would have been more accepted. Our next category are trusses. A truss is made up of a web of triangles joined together to enable the even distribution of weight and the handling of changing in tension and compression without any bending or shearing, so that the overall assembly behaves essentially as a single object. An example, for instance, of a truss using Corbusier's design would be the Maison Dome, maybe less noticeable, but within the roof there's a truss system, and typically you would want to use truss to achieve long spans, minimize the weight of a structure, reduce deflections and support heavy loads. An example would be, for instance, the Golden Gate Bridge, where there's clearly a lot of trussing happening on there because it serves a pure, simple, direct structural purpose. But an example of something that can do that with a bit more, perhaps, architectural swagger would be three-dimensional trusses, and those would be space frames. Space frames being a lightweight, rigid roofing system where a series of connectors are joined together by cords or struts and with bracing members. Their strength derives from the rigidity of the triangle, with the flexing loads being transmitted as tension and compression loads along the length of each cord. Most space frames are constructed using structural steel or aluminum alloy tubes. Finally, when we're looking at architectural history, it's very interesting to see that in the 1970s, trusses were very much in vogue. If we look at the work of Yona Friedman or Cedric Price, they were always imagining a world that was very high-tech. And to imagine a high-tech world, the employment of the architectural feature of trusses was often used in representation. Frames are essentially the structural skeleton of a building. Most typical buildings are going to see a concrete frame or a steel frame to support the project. In construction, the term frame typically refers to a rigid structure that supports a building or other built assets such as a bridge or tunnel or parts of it. A lot of the housing built in the United States, for instance, from the 19th century to the mid-20th century, used balloon framing. This technique was popular at a time where timber was made readily available. A more outlandish and creative use of the frame potentially would be, for instance, all the works from Buckminster Fuller, and I'm thinking in particular the one for the Montreal exhibition where it's a massive geodesic dome. Now it's interesting to look at frames because they're essentially the skeleton of a project, of a structure. Brazilian artist Henrique Oliveira, for instance, really turned this concept on its head by creating in this frame really interesting surrealist trees that would grow up from the beams and from the columns in this half sculptural, half architectural installation. This next category is often quite scary or confusing for anyone who jumps into the world of architectural engineering, and those are cables, nets and membranes. A cable is a line made of rope, chain or wire, for instance, that has different functions according to the application it is used for. It can either tie together 2 points or simply connect them. For building design though, they can be load-bearing and non-load-bearing, but they are typically used for net and membrane combination. An excellent example of this would be, for instance, the O2 Arena by the late Richard Rogers, a beautiful project where essentially the membrane is held up by loads of cables. An example for nets would be, for instance, by the German architect Freyotto for the Munich Olympic Stadium, creating this interesting, complex weaving system of nets and cables. And to go back onto the O2 arena, looking specifically at membranes, it's interesting to see how something that could be so lightweight can become so efficiently structurally and can start to actually compose a space. A really interesting adaptation of the membrane is, for instance, by Lambert Camps, who created this bridge called the air bridge, where essentially no hard materials are needed, but just by pumping air, it can create this passage between two spaces. It's this multi-layered inflatable building that really starts to question the use of membranes in architecture. Now to our final category, arches, domes and shells. Arches, domes, shells, and even vaults are structures that work in compression to divert gravity load to the sides in order to create occupiable spaces. A dome is basically an arch that's been rotated around its central vertical axis, and shells are a thin curved plate structure with a bit more plasticity. Now perhaps Roman aqueducts are one of the most famous examples of how to use arches practically, and to this day still are a marvel of architecture. In a near completely different manner but still structurally relevant, we could look at the Maison Jaoul by Corbusier, with the roof having some sort of arched member. An interesting example from classical architecture, you might have seen the Florence Dome by Brunelleschi, is that interestingly the detailing for it also was problematic. Due to the unreinforced masonry that Brunelleschi used for the dome, its weakened tension, which leads to cracking when tensile stresses exceeded the limited masonry tensile strength, which means that essentially the building is susceptible to a lot of damage if there's any seismic implications happening in Florence. A modern reinterpretation, for instance with the conservatories by Wilkinson in Singapore, where essentially it's a composite structure formed of a grid shell that works in tandem with external superstructure of radially arranged arched steel ribs. Now, they were introduced primarily to address the lateral loads to the grid shell, but they also give the conservatories, of course, a distinctive organic look. One of my favourite precedents when talking about shells in architecture is the TWA Centre by Eero Saarinen, which needed this shell structure so that it could somewhat imitate a bird in flight. Now, this was quite fitting as the building's purpose was an airport. But perhaps the grandfather of shell structures would be Felix Candela. Felix Candela was an amazing architect slash engineer, where he would be able to create these incredible shell structures without the use of computation, purely through the mathematics of material. The projects are interesting not only in the final outcome, but also in the way that they were built. The construction process, for instance, for these shells are amazing when we start to look at actually the scaffolding that had to be put in place to create. Through his projects, he was able to push the material to its utmost limit, creating this almost surrealist projects and constructions using concrete the thinnest way possible, pushing the material to its absolute extent. So thank you for watching this short video about basic structural components and forms. Hopefully it gives you an understanding of, if you're a student, what elements you should integrate to your projects and how they serve the physical and engineering properties that are needed. But if you're interested in architecture in general, hopefully it gives you a bit of understanding of the spaces you're in and you're more aware of your environment. I hope you guys have a good morning, afternoon and evening. Bye bye.